The infrared spectrum for methylbenzoate is shown below. Which peak corresponds to the carbon-oxygen double bond of the ester? So when we're looking at an infrared spectrum, we have learned how to analyze from roughly about 1500 up, okay, to about 4000. And we've learned how to divide this IR spectrum into some major regions. So the first major region that we've seen in this upper part of the spectrum is where we have bonds to hydrogen. So that's going to be from around here on up. So these are going to be different types of bonds to hydrogen. That's not what we're looking for. We're looking for the carbon-oxygen double bond. The next thing that we've learned to look for right in here, 21 to 2200, give or take, somewhere in that range, is the triple bond region. And we don't see anything in there labeled because we don't have any triple bonds in methylbenzoate. And then the next region that we're going to see down here is the double bond region. So in this question, we're being asked specifically about the carbon-oxygen double bond of the ester. So those are usually around 1700 is where you find carbonyls, give or take. And carbonyls tend to be really intense because they're really polar bonds, right? So this 1724 looks like our carbonyl. So we can go ahead and select that answer, but let's also make sure we can label everything else in the spectrum so that we know what we have. Right, so the other double bonds you're going to see in this molecule are in that benzene ring. So that's what we're seeing right there at that 1602 is your benzene ring. And then these other sets of peaks are in your bonds to hydrogen region. So we'll take a minute and label these because we've got two different types of bonds to hydrogen. We've got carbon-hydrogen bonds here that are sp3 in that part of the molecule. And then on your benzene ring, we've got all of these hydrogens. And then all of your carbon atoms of your benzene ring are sp2 hybridized. Okay, so what we tend to see is that the sp2 carbon hydrogen stretches are these ones that appear just above 3000, and the sp3 are these ones that appear just below 3000. Right, so 3000 is your dividing line between those two. Okay, so we've answered that. One other thing I want to mention with this carbonyl of the ester. So this ester here is conjugated, which is going to lower the stretching frequency a little bit from an ester that is not conjugated. So this is a conjugated ester. And so that conjugation lowers the stretching frequency because you've got resonance. And what this resonance is doing is making it so that that carbonyl is not a pure double bond. It is somewhere in between a double bond and a single bond. And so we can see that when we draw out the resonance. And of course we can draw more resonance structures around the ring. So I'm going to say there's more ... Okay, so conjugation lowers the stretching frequency. So you might see a non-conjugated ester maybe more like 1740, this one being a little lower because of that resonance.